your attendances. Hopefully. Okay. So today, as I planned, we are going to discuss um, field theory, or rather classical mechanics in continuous medium. And we will see that the classical mechanics, the principles that I learned in classical mechanics goes beyond um, the limited scope of point particles. So it's not only point particles that can be dealt with classical mechanics. If you are observant enough, then you can do perhaps more sophisticated things. And today we are going to discuss one of those. Okay, so let me start by writing. This is classical mechanics in continuous media. So again, I will be following the book by Goldstein for this part, which I think the introduction is nice in that book. So it starts with an example. Okay. The example is that of a one-dimensional elastic rod. So the example at hand is that 1D elastic rod. Okay, and especially the propagation of waves in that rod. Okay, so propagation of elastic waves. Okay, now uh, for all intents and purposes, if the rod is like macroscopically large, then I will consider the length of the rod to be infinite for practical purposes, as long as we are focusing and we are not focusing at the very end of those rods. This approximation holds true. So what you have here is that you have a one-dimensional rod. So it goes both way, and propagation of elastic waves in that rod. So suppose there is a sound wave that is being propagating, and it is being a longitudinal wave. So you can think of it a metal bar, and mm, so you want to study the propagation of elastic sound waves in that rod. You perhaps already know that how it behaves. I mean, perhaps this was part of your undergraduate syllabus. But anyway, we will try to have a new perspective on this problem. The perspective from the Lagrangian and Hamiltonian mechanics that we have learned. Okay. So we'll start slow and then pick up a bit of pace. Okay. So the first thing you do is that you discretize this rod, because so far you have learned the mechanics of point particles. So a particle that is moving under a force field or a potential certain. So the first thing I ask is that can this continuous can I imagine a discretized version of this continuous rod? Okay, so here is it. Here is one of the way you can think of it. So you can think of this rod as an array of, say, point particles. The let's say the atoms of this uh, of this bar, which are connected by this identical spring. Okay, and then here, and so you get the idea. Now the separation between any two point particle, I will call it A. Of course, this A is very small. This A, I will take the limit a tends to 0 at the end of the day. And these are identical mass particles, so I will denote the mass of this each point particle to be m. Okay, and the spring constant that connects the 2 points, the spring constant will be denoted by k. Okay, so these are my things. So this elastic rod can be thought of as like an infinite number of mass points, each of them connected by these springs. And when a wave propagates, so communicating from one mass particle to the adjacent particle, uh, this propagates through the spring. So that is, you can visualize that it basically the longitudinal wave is basically propagating via these springs. I mean, you can visualize it easily, perhaps. And let us assume that this is the ith particle. So this is the index for this is let's say I. This is my then I plus 1, and this is of course I minus 1. And at any instant of time, let's say at time t, these will be displaced from this from its equilibrium position. So at time t, if I say that this has been displaced, and the displacement is I denote by eta with the index of the corresponding particle, and this has been displaced here. It's eta I. So this eta I has nothing to do with eta I plus 1. So these are independent displacement that these particles have undergone. Okay. And similarly, this is eta I minus 1. Okay. So the particle is now here. Okay. Rather, and it goes on. So now, if I try to write down the potential energy of that system, so the any deformation of the spring, say for this spring, okay, or let's say this spring, would be given by the difference of eta I and eta I plus 1. Okay. So remember, these etas are sensitive to signs. That means if eta I is negative, that means the particle is being deformed towards the left, and if it is positive, then it is deformed towards the right. So for this spring, let's say if I call this for the ith spring, the Vi will be so k by 2 into eta I plus 1 minus eta I whole square. Okay. So that is my potential energy. So the total potential energy would be given by V equals to k by 2, then summation over I, this all the spring that are there in here, and this is eta I plus 1 minus eta I whole square. All right. So, and the kinetic energy, of course, would be the sum of all the kinetic energy, that is m by 2 summation of I eta I dot square. That is my kinetic energy for ith particle, and then you sum over all of those. So your Lagrangian, in the traditional sense, in your discrete particle mechanics, should be given by T minus V, and that is half summation over I m eta I dot square minus k into eta I plus 1 minus eta I whole square. So let me put a different bracket here. That is my Lagrangian. Good. And I would like to write this Lagrangian in a more fancy way that I'd be using later. So I would be writing this as half summation over I, then A, okay, and then then M over A, then eta I dot square minus K times A, eta I plus 1 minus eta I over A whole square. That's it. Okay. And the thing inside the square bracket, I will call it A li. So this is just this expression written in a different form. So I have taken out this A here. The A is the like the interatomic spacing, if you want to think about it in that way, in those terms. That is it. Okay. Now, if you want to find the Lagrange equation for eta I, you can find it easily from this Lagrangian. So the Lagrange's equation for eta I, okay, because these are my now independent coordinates, right? Because I have infinite number of independent coordinates. Notice these things. These are my independent coordinates because my Lagrangian is a function of this eta I and eta I dot. As I know, then I can find out for the ith coordinate, that is eta I can find out the Lagrange's equation. The Lagrange's equation would be given by, so m by a eta I double dot minus k times a eta I plus 1 minus eta I by a square plus ka eta I minus eta I minus 1 by a square. Yeah. That is equal to 0. Okay. Now I want to connect, so I want to find out the interpretation of this K. Okay, what is this spring constant actually means? So remember, it's a continuous elastic medium. So I have, for my convenience, so that I can apply my knowledge of discrete particle mechanics here, I have imagined a discretized version. But at the end of the day, I have to take the limit a tends to 0. Okay. For that, since it is an elastic medium, I know that elastic medium or the elastic rod follows Hooke's law. So the Hooke's law actually is that the restoring force is given by the Young's modulus y times the strain. Okay, so this is my strain. Sorry, I forgot which one is stress and which one is strain. I think this one is called stress and this one is strain. So anyway, this is basically deformation per unit length. Okay, so deformation per unit length. Okay, so now the deformation of a certain segment of spring is, let's say, the ith spring, which is here. So the deformation is eta I plus 1 minus eta I, and the length of the spring is a, or the length of that segment is a. So in my language, this is eta I plus 1 minus eta I over a. Okay, so this is y by a, then eta I plus 1 minus eta I. But because of my springy approximation, my restoring force in other way can be thought of as that the k times the deformation. Okay, so this is k times eta I plus 1 minus eta I. That is the restoring force. That's same. And that gives me a relation between this k and the Young's modulus. So that allows me to write that k is essentially the Young's modulus by the length, or I can write y equals k times a. Okay. So that is why I have kept this thing visible, that these k times a is basically my y also. Here is the y. Now let us come to the continuous version of this thing. Okay. So in the continuous version, this m by a should be replaced by the mass per unit length. Okay. It's the linear mass density. So you call it, say, mu. Okay. So this is your linear mass density, right? Okay. So that is mu. Ka is that, and in the continuous version, basically, so eta has a value. So this I, what is this index I denoting here? So I denotes the position of that particle at the position of that particle at a certain space-time point. Remember the important phrase is a certain space-time point. That means the condition of that particle at a certain location, at a certain x, okay, and at a certain time t. So this eta I is basically becomes eta xt. That means the deformation of the segment that is at location x at time t. Okay. So the deformation of the segment that is at location x at time t. Let me write it down for you. So this is the deformation of the segment located at x at time t. Okay. So this is the continuous limit, or the continuous interpretation of eta. Okay. Now so then of course eta I plus 1 minus eta I over a, when I take the limit a tends to 0, this is the space derivative of eta. Okay, I will write it as del eta del x, right? So this is my del eta del x. Okay, so let's say this is the value of del eta del x at location I. Okay, that means the ith site. This is the value of del eta del x at location ith site. Okay. Again, so now look at these two terms. So you take one a out, so that this is basically y or minus y times, this is the 1 by a times del eta del x at ith location, minus, again this is 1 by a times, this is also del eta del x, but at the I minus 1th location. If that is my ith location, then this must be at I minus 1th location. So this is also del eta del x at the location I minus 1. Okay. So what is this thing again? So this is the double derivative again. So this is again, if you take limit a tends to 0, then this is basically the value of del 2 eta del x2. Okay, that's it. So this is minus y del 2 eta del x2. Okay, so the equation you get, the equation you get is, so notice that, so this is del 2 eta del t2 minus y times del 2 eta del x2 equals 0. So let me write down the equation. So the equation of motion is mu times del 2 eta delta 2 minus y del 2 minus y del 2 eta del x2 equals 0. So you can write that is basically del 2 eta del t2 is equals square root of y by mu whole square del 2 eta del x2. Remember, in this version, this eta is a function of x and t. Now, of course, this looks like a wave equation with the wave velocity being square root of y by mu. Okay, but note the crucial difference from point particle mechanics here, or the discrete mechanics here. So the thing I have obtained, so I had so L, the total Lagrangian, was a function of infinite number of degrees of freedom. So all of these eta i's were independent, right? So the displacement of my ith side does not depend on the displacement on any other side. Okay, so these were my independent coordinates. These were my independent coordinates, and we had infinite number of them. But at the end, actually, apparently I got a single equation, but that is an illusion. So because eta at every point x and t satisfies this equation, so this is essentially an infinite number equation, because eta at every location satisfies this equation. But now if you change your point of view on how to look upon these kind of problems when continuous medium is involved, so you do not think of eta to be a independent coordinate anymore. Okay, and you just say that eta is a field that has a value at every space-time location. Okay, so this medium, this continuous rod, is the properties of this continuous rod would be determined if I specify the field eta at every space-time point. Okay, so any continuous medium, let's say any continuous medium, can be described by a sort of a field. By field I mean, so it has a certain value at a certain space-time point, at a point in x, and at time t it has a value. Okay, and it is continuous. Okay, so it's the same as electric field and magnetic field. So in general, field means something that has a functional form and which has different values in space-time points. Okay, so now first of all, I also note that thinking in terms of field gives me some interesting aspects of Lagrangian mechanics. First of all, I see that the derivatives in terms of space and time are treated symmetrically. So both of them are basically del 2 over del x2. So the distinction between space and time are not, like, time derivative is not any more spatial than the space derivative. So space is also becomes another implicit coordinate, if you may like, if you would like to think that way. Okay. The thing is, also you notice that this x and t are independent parameters now, or the kind of the independent coordinates now. So remember, in point particle mechanics, x used to denote the position. Okay, x used to denote the position, and the x was an implicit function of t itself. So let me again, so difference with discrete mechanics. Okay. So if I kind of put the vague notion of the, say, one-to-one correspondences in these things. So remember, I had these generalized coordinates, and the time was an implicit variable that was contained in Q. So in discrete mechanics, this Q was kind of physically interpreted as your position, and time was just time. Okay. So basically, Q is equivalent to X, and T is equivalent to T in discrete mechanics. Okay. But in continuum mechanics, Q is equivalent to these eta fields. So these is equivalent to, say, eta xt, or rather, yeah. And that T, that implicit variable, is equivalent to all of them, x and t. So x, y, z, and t. So the coordinate and time are like basically the implicit variable. And more importantly, these x and t are independent of each other. Okay, so these are independent of each other. Okay, so these are not correlated variable anymore. Okay, so that enables you to interchangeably use partial derivative and total derivatives. So this del 2 eta del x2 can become, like, you can interpret it as d2 eta dx2, and this is just your d2 eta dt2, if you wish, because now x and t are independent variables, so you do not need to distinguish between the space derivative and the time derivative. So since in the case of discrete mechanics, this x was implicitly dependent on t, you needed to distinguish between, say, del x and d dx, but here that thing is gone. Okay. Now the question is, so this is kind of my Euler-Lagrange's equation for continuous medium. But how to consistently obtain it? I cannot just figure out for every possible continuous medium. I cannot do the same exercise, like discretizing the version first and then taking tends to 0, because this one-dimensional rod is a special thing where my intuitions work, and I could figure out a discretized version, and I can draw my intuitions in that. But for general problems, let's say problems with electric and magnetic field, like how would you even discretize that? How would you consider a discrete version of electric and magnetic field? So we need to slightly get a more direct formalism where this kind of equation of motion can be obtained directly, and that is where this helps us. This one. So this, if you notice this, I wrote this thing as basically summation over I a times li. So in li, the half is contained in li. Okay. So notice where li is my Lagrangian in the ith side. I can think about it as my Lagrangian at the ith side. Okay, so at the ith location. So in the continuous version, what will happen? So if my L is equals summation over a times li, so the total Lagrangian would be then given by, so integration of dx. So this summation over a becomes integration over dx, and this L becomes, so this li becomes I will call it the curly L, which is also a function of eta and eta dot, let's say. Okay. How do I do that? I will say this. This is the continuous version. I have just changed the notation. I have just wrote li in the continuous limit as curly L is a function of eta and eta dot. Remember what was li? So li was half m eta dot square, sorry, m by a eta dot square, right? What is this? Yeah. So half m by a eta dot square, then minus k eta I minus eta I. So you can get it from here. So this m by a is just mu. So this eta dot is just d2 eta, sorry, d eta dt whole square, minus k is the Young's modulus, and what is this? This is d eta dx whole square. Okay. So I can write this L eta dot equals half mu d eta dt whole square. I should not just write eta dot, sorry. I should also write like all the derivative of eta dot. So eta dot and d eta dx, of course. Because now my x and t are treated separately, not like individually. Minus half y d eta dx whole square. Okay. And this thing I will call my Lagrangian densities. Okay. So this I will call my Lagrangian density. Okay. And it is in general a function of eta d eta dt d eta dx, and it can also explicitly depend on x and t, of course. But again, in the same way that we focused on Lagrangians in discrete mechanics that was not explicitly dependent on time, you will here deal with Lagrangian densities that does not depend explicitly on the space-time coordinates. Okay, so why do I call it Lagrangian density? In the same way I call my m by a to be my mass density. So in the same way I call m by a to be my mass density. So this L by a, L over a, okay, would be my Lagrangian density, because the total Lagrangian should be given by the space integration of the Lagrangian density. So if you are looking for the three-dimensional version, so for the 3D version, your total Lagrangian would be given by this is d3x, or I will call it like d3x, and then L is a function of eta and the derivatives of eta, which I will write it as del mu eta. Okay, so the field and its derivative. So the Lagrangian density is now of a function of the fields, the quantity that I called the field, and the field derivatives. The advantage in working with this Lagrangian density is that you can figure out an easy way that this Lagrangian density is a Lorentz invariant quantity. Okay, how do you see that? Because you remember that that S, the action was integration of L dt. Okay, so if you multiply, so if you substitute L from here, so this is basically becomes d4x, because d3x times dt is the d4x times L eta del mu eta. Okay. Now, first of all, this S is a Lorentz invariant quantity, because it you raise it to the power e to the power I s. Okay, and so now since d4x is a Lorentz invariant quantity, I am not sure if you have learned this in your special theory of relativity course, but it is easy to see. So d4x basically tells you this is dt dx dy dz, and in a different frame of reference, let me say that this is dt prime dx prime dy prime dz prime, Now, if the motion is along x direction, let's say, then and this if dt is the proper time, which is the rest frame, then this will get time dilated. So this dt prime will be just dt over 1 minus beta square, and dx prime would be contracted, so it would be dx times square root of 1 minus beta square. So these two factors will cancel out, and it will give you that the four-dimensional volume is still Lorentz invariant. Okay, and this action needs to be Lorentz invariant because this action relates to the quantum mechanical probability amplitude. So let me not get into that for now. Okay, so since this is Lorentz invariant, and for some reasons, let's say S needs to be Lorentz invariant, this L also needs to be a Lorentz scalar. Okay, so L should be such that it should not contain any free index. That's why, although L is a function of eta and del mu eta, it will never contain del mu eta alone. It has to contain. So if you try to write down L, it will always contain terms like this, because del mu eta times del mu eta, so that this mu and mu, these two indices contract, and you are left with a Lorentz scalar. Okay, so that's why it comes in a pair. So the whole point of continuum mechanics can be dubbed into this Lagrangian density, curly L, and this from this Lagrangian density, if you again apply your variational principle, then you can figure out the equation of motion for that. So let me do it for a let me say for a one-dimensional system, so 1D system again. So for 1D system, this L will be a function of eta d eta dx, okay, and let's say d eta dt. For now on, I will ignore the explicit dependence on x and t, because those are rarely be our scenario. So it's the function of field derivatives. Then your action is basically integration dx dt, and then L, right? So now you want to move from point x1 t1 to x2 t2, and you want to find out the condition for this S to be minimum. So your first lecture, variational principle. So what should be the condition now? So what should be the correct eta xt? Okay, let's say. So what is the correct eta xt you will have? So again, you will deviate from the correct eta xt by infinitesimal amount, and then take the derivative to be 0, and you do the same exercise, and then you find the equation of motion that you get is given by this. So the equation of motion, okay, is given by d dt of del L del of d eta dt, okay, that is basically eta dot, plus d dx, then del L del of d eta dx minus del L del eta equals 0. So this would be your equation of motion. Again, you see that, so given a Lagrangian density, you do not know what it is, but given a Lagrangian density like this, you can find out that from the variational principle, the equation of motion should be like this. So if you apply this equation of motion to the Lagrangian density that I figured out here, so if you apply to this Lagrangian density, you will find precisely this equation of motion. So that gives me a more abstract sense of nature. So that means that for this one-dimensional continuous rod that I started with, I do not have to every time do the laborious job of discretizing the thing and then take my intuition from there. So I can like invent a black box. Like I do not have to think what I am doing. I mean, of course, I have to think to some degree, but if I can guess somehow this Lagrangian density, so what I do is again guess from symmetry principle. So if I can guess somehow this Lagrangian density, then I will get my equation of motion. I will apply this and then I will get equation of motion. So how do I explain the elastic wave propagation in a rod? Just try to guess the Lagrangian density. So for the one-dimensional rod, what you can guess is that, so this you can guess. So this is your kinetic energy density. So I call it say curly T, and this is your potential energy density, and you call it curly V. So if you guess that Lagrangian somehow, you do not ask question where this Lagrangian came from. But if you guess the correct Lagrangian for that system in terms of the field, you define a certain field there. Then the field equation. So this is also a field equation. The wave equation is a field equation, and that basically the field propagates as waves. Okay. There is another interesting example, of course, of that. So if you can guess that particular Lagrangian and you apply that equation, you will get a very interesting equation. Suppose, where did I? Let me find out first. Where did I write that? Here. Okay. So suppose now I have a field. I call the fields to be psi xt and psi star xt. So there are two independent fields here. So psi and psi star should be treated independently because this is a complex field. So it has two components here. And in terms of this field, I write a Lagrangian density, okay, in one dimension, let's say. So what I have is the Lagrangian density is equals, where did I write that? Here. Put it towards, oops. Yeah. So L equals minus a square over twice m. Then there is say d psi dx into d psi star dx, okay, plus, I don't know if it is plus or minus, but I think it's plus v psi star psi, and then plus h cross over twice I, then psi star d psi dt minus psi d psi star dt. Okay, so if this is my Lagrangian density, okay, and you use the this equation of motion, okay, so you will get two equation of motion. So equation of motion for psi and psi star. So equation of motion corresponding to psi star, where eta is replaced by psi star. Check that you obtain the Schrodinger equation. Okay, but you might say, was it possible so you might say that since I knew Schrodinger equation already, it was easy for me to get to this Lagrangian. But if I did not know about Schrodinger equation, could this could this formalism allow me to write down Lagrangian for corresponding to Schrodinger equation? To some degree, it could, because if you start with psi and you want to interpret psi as the probability amplitude, then you know that in the wave function there is a rephasing invariant. So if you modify the wave function by a phase, your physics should not change. Okay, so first of all, at least you get the idea that that the psi star and psi should come in combination, and never you should get any terms which only contain psi or only contain psi star, because that will not be phase invariance. Okay, so the phase will be there. This type of prefactors is also easy to guess. It's from the dimensional analysis. So remember, if you are doing one-dimensional thing, then this S has the dimension of angular momentum, and then this dx and dt has the dimension of length times time. I don't know what that is. So the dimension of this Lagrangian density should be the dimension of angular momentum divided by this. Okay. Now, since you also impose that integration psi squared dx equals 1, and that gives you the dimension of psi is basically length to the power minus half. Okay. So if you introduce these dimensional arguments here, you will see that you need to multiply these quantities. So these quantities by something that has the dimension of energy, which you call the potential energy. This quantity with something which is the dimension of this. So you introduce two fundamental constants there, and so on and so forth. So that means the physical laws that we are trying to describe later, say the laws of electrodynamics and this thing. Again, so for the laws of electrodynamics, yeah, that is one other interesting interesting example. So I showed you that electrodynamics is something that is by nature gauge invariant, and we found out that F mu nu is gauge invariant. Okay, so I can write down that L should contain F mu nu, but L must be Lagrange invariant also. So this mu and nu cannot be free. So the only thing you can write is basically F mu nu times some factor. This is the factor of convenience. It's a normalization of the kinetic term when you do quantum field theory. But you can get the essential part that this Lagrangian for electrodynamics, at least for free electrodynamics, for free version of the Maxwell equation, without doing even any experiment. So this is the perfect example. So without doing any experiment, if I have the formalism of this Lagrangian density from which I am going to get my equations of motion using that, I can obtain from symmetry principle. So I demand a theory which is invariant under gauge symmetry, and F mu nu, I learned that it is invariant under gauge symmetry. But the Lagrangian density should also be a Lorentz scalar, so it should not contain any free Lorentz indices. So the only thing that I can write, I just contract F mu nu and F mu nu, and that gives me the Lagrangian density for electrodynamics, and from that everything follows. Okay, so that is kind of that's a quick introduction. Okay, not so very nice introduction because I skipped a lot of details and you have to self-study. But I hope that you got an essence of what kind of powerful technique lies behind this this thing which I call classical field theory. So for just like in classical mechanics and discrete classical mechanics, we try to get the Lagrangian by hooks and crooks, by one way or the other. We try to get the Lagrangian. Okay. Once I get the Lagrangian, so Lagrangian is anything. As I told you, Lagrangian is not necessarily t minus v. T minus b holds to a certain degree when your forces are conservative and things are intuitive. But for a vast majority of system, the complicated system, Lagrangian is something else, and that you have to guess wisely from symmetry principle or other principles. Okay. In the same thing, in the same way, I notice that when I am dealing with the continuous media, first of all, it lets me to uh, uh, have my space and time coordinates being treated in a similar fashion, in a symmetric fashion. So a relativistic formalism is more easier to get. And again, I land upon the same kind of conclusion that if some way or the other I can get the Lagrangian density for a system, for a continuous system, and that is described by a field. Here I introduce certain field, because for electromagnetic thing the field is a mu. Okay, so this is a mu xt, that is your field. Okay, then you get everything. So any complicated problem you want to solve on higher physics that you do not have an intuition on, it does not look like a rod, perhaps it has to do with quarks or vibrating strings or whatever, you try to get the Lagrangian density, or rather the action. Okay, it's the same thing. If you get the Lagrangian density, you get the action. And how would you guess it? What kind of principle you would you use to guess this curly L? That's it. Okay. So now I understand that there might be many questions, so you can ask now. And,
Sir,
yes.
sir, in this page, the curly L is minus h squared square by 2. You found this by using equation of motion, or by how did you write minus h squared square del c by del x, sir?
To some degree, yes. Since I knew Schrodinger equation, then I also knew what kind of curly L would give me the Schrodinger equation. But this particular nature of the prefactor would be we would get from dimensional analysis. As I told you, I know the dimension of curly L, which is the dimension of angular momentum by dx dt, and psi has a dimension of L to the power minus half. So d psi dx and d psi star dx should have a combined dimension. You compensate the remaining dimension that you will need to get the dimension of L, and the dimension comes out to be angular momentum square by mass. Okay, this 2, of course, I got from hindsight. This minus sign, of course, I got from hindsight from Schrodinger equation. But like the factor h square by m, that the prefactor should be h square by m, comes from dimensional argument. You can get it from dimensional argument.
And sir, what about the last term, h squared by 2y? So
Again, the 2i comes from hindsight, but h cross comes from dimensional argument. Okay. This has among, so you will see that if you do this, then the remaining dimension, just do it, so you find out the dimension of Lagrangian density in terms of MLT. You find out the dimension of this quantity in terms of MLT, and try to figure out what is the remaining dimension that needs to be dumped into this factor. Okay, so and if the quantity is angular momentum, then you already know a fundamental constant that is the dimension of angular momentum, and you plug that in.
Sir, similarly, we can do any independent. Here you took psi and psi star are independent fields. Similarly, we can do any for any fields. I mean, for any independent fields.
Yes, whenever there is a continuous system at hand, for example, in the next, in the example of the electromagnetic field, this is your field. So you have basically 4 fields: A0, A1, A2, and A3. Okay. The magnetic vector potential, the 4 vector potential, those are your fields. So you have kind of 4 equations of motion. So one for A0, one for A1, one for A2, one for A3. Is that clear?
Yes, sir, but a bit confused. But sir, actually, this is vast to us. But later on, when we'll go through the book, then that will be more clear. But till now, got it, sir.
Okay. Anyone else?
Excuse me, sir.
Yes.
Can we define like other things like a Hamiltonian equation brackets for this continuous case? Can we go further here?
We can. So I did not cover it in the first one. There are ways to define Hamiltonian. Perhaps I will take an extra lecture and I will kind of sketch on that. But it's not so straightforward. So let me just give you a hint, and then so for example, you can define a generalized momentum or the momentum density pi in terms of that. So it would be obvious generalization of your classical mechanics. So this is basically P equals del L del Q dot. Okay. So in the same sense, so Q is replaced by eta, and Lagrangian is replaced by Lagrangian density. Now, so that's why this pi is called the momentum density. Okay. And then you can define something called a Hamiltonian density in the same spirit as that. And that would be given by pi eta dot minus L. Now, you have to be careful when you are working with a Hamiltonian density in continuum field theory, because as soon as you define your Hamiltonian density, you see that the time derivative again gets priority. There is no space derivative here. Okay. Again, it's just pi eta dot. So this symmetrization of space-time coordinates again gets destroyed, and you have to be taking special care so that uh, a relativistically invariant formalism is done there also. And for Poisson bracket, again, it is not so straightforward, because remember, this pi is a density. So I had a Poisson bracket between Q and P, which was 1, right? So similarly, you might find this pi and eta equals to something, but it will not be so. Remember, the pi and eta has different meaning here. So this pi is a density. It's like a momentum density. But eta is not a density, eta is a field. Okay? Eta is a field which has values, and you do not have to integrate eta over volume to get something. Eta is what it is. You do not have to integrate over volume. But to get the momentum, you have to integrate pi over the volume. Just like you have to get the total Lagrangian, you have to integrate L over the volume. And that's why, like, this pi and eta in many different ways are, let's say, two different things that cannot be directly correlated with that. So when you are defining Poisson bracket in case of continuous field theory, you need to be careful, let's say. And this is indeed the reason, at least in particle physics, we stick to the Lagrangian. Okay, we do not. So we do our calculation using this Lagrangian density. So by Lagrangian, I mean Lagrangian density. And in most of the quantum field theory text, all the calculations of scattering, decay, Feynman diagrams are done using Lagrangian, because this is straightforward. Although that's a second order equation of motion, but since it is clean, and it, like, direct one-to-one correspondence can be made from your usual Lagrangian density, it's much more intuitive to work with Lagrangian than in Hamiltonian when you are doing field theory. Okay. And there is also an interesting connection, just in the same way I made a connection between classical mechanics and quantum mechanics when it came to Poisson bracket. It's basically assigning different meaning to those Poisson brackets. We just elevate them to commutator. So the same thing can be done here, and that takes you from classical field theory to quantum field theory, but that will probably take long, and I will not be able to cover it here. Okay. So then let me schedule a class on Saturday. So let's say we meet on Saturday at 3 p.m. this Saturday. Is that okay with everyone?
Yes, sir.
Okay. So no other conflicting schedule, right? So then, yeah, so that would be my last class. Then I will discuss these things further. I mean, these things are new. Unless you study it really well, you are not going to understand anything. I mean, these are new concepts. I mean, these are very interesting concepts. I think, yeah, I mean, you will achieve great things if you learn it right now. It will help you in your courses, in your future courses. But yeah, you have to read it. Okay, any other questions then? All right then. So I stop recording now.